So the idea for this session is that you're going to sit there and read the first half of the paper today, and then we'll discuss about it. And then next week, you'll read the second half of the paper and discuss about it. And some people might say, oh, that sucks. I mean, why are we just going to sit there and read? Well, you should think of it as similar to, making an appointment with a bunch of friends to go to the gym. It gets you there, and then you do your workout. Even though everybody's doing their workout all by themselves, you're still working in a group. And then after we read it, we'll discuss in a group, and that's the time when you'll really get something out of this. But I think it's valuable just to sit yourself in a chair and say, for the next hour, I'm going to read this paper, even though it's silent reading, but you're going to get the benefit of discussion afterwards. So it might seem weird, but it does work. I've done study groups like this, and they do work. All right, so for today, we're going to look at this paper. I'd like to say a few words first about the paper. Notice that the title, let me share it again. The title of the paper says, the matrix calculus you need for machine learning. It's a little slow here, but it's going to share in a minute. There we go. You should see it now, right?
Yes.
Yeah, thank you. So it says the matrix calculus you need for machine learning. It doesn't say all the matrix calculus you need for machine learning, but this is most of it. And once you learn this and you learn it well, you'll be able to learn whatever else you need, the rest of it. Okay, so that's the advertisement for this course, for this little review. So what they've done is they've broken down this, this part of matrix calculus into a bunch of sections here. And it's really nice the way they've organized it. First, they review the scalar derivative rules. This is basically the starting point where everyone is probably here now. You know about how to take derivatives of scalar functions. And you know this stuff. This is probably the starting point. The derivative of a constant, the derivative of a constant times a function, the derivative of a power, the derivative of a sum, difference, product, and then the chain rule. These are all the important sort of prior knowledge that we expect you to have if you're going to study this thing. And but it doesn't require a lot more than this. So you don't really have to have had a whole year of calculus. You just have to be sort of basically, familiar with the basics. And that's what we'll need to dive in. So if you look through this paper, it can be really intimidating once you get into the formulas. You see all this stuff with all these weird Greek symbols and very dense mathematical expressions like this. And it gets worse. And so it's very intimidating, or it could be very intimidating if you haven't seen it before, especially stuff like this. Well, what's this circle? Well, we'll find out something about this. So it can be really intimidating to look at this. But what I want to tell you is that by sitting here and working on this, studying it, you won't be intimidated for long, because all this is a very fancy notation that helps to make the kinds of calculations we need to do in neural networks. It makes those kind of calculations really smooth, almost effortlessly smooth. So there's a little bit of a learning curve to learn this notation, but once you've learned it, then you'll see that this stuff isn't as intimidating as you might have thought. Okay, so I guess the first thing I want to do is sort of give you an overview. I'm sort of scrolling through to see what we're doing, the way it's organized, and let me back up a little bit. So we started with the section 2 on just reviewing the scalar differentiation, which you already probably know something about, right? This is the rules of scalar. So then he says, okay, now let's start talking about what happens if you have to differentiate a vector, and what happens if the function is a function of more than one variable. So there are these two new concepts we have to incorporate into our study. We have to learn how to differentiate vectors, and we have to learn how to differentiate functions of more than one variable, not just f of x, but f of x, y, f of x comma y, or f of x, x1, comma x2, comma x3, these kind of functions. And so it introduces you to what these are, what these multiple variable functions are. Like here they talk about f of x and y is 3x squared y. That's a multivariable function of two variables. So we have to learn how to differentiate those. And then they introduce this concept of gradient. And the gradient is nothing more than a way to organize a derivative of a multivariable function. So it organizes the partial derivative. So the idea is that you have this concept of partial derivatives, which is this backwards 6 kind of notation. And that kind of looks like a derivative, but it's a little different. It says differentiate the function with y remaining fixed. Just differentiate the function as if it only depended on x. So, you know, if you want to differentiate 3x, whatever our function was, forget what the function is, 3x squared y, we pretend that f of x equals 3x squared y, where 3 and y are lumped together to be the constant. And then we just differentiate with respect to x. To x. And then when we do partial derivative of f with respect to y, we regard x as part of the constant, the dependence on x as part of the constant, and we only differentiate with respect to the dependence on y. So that's what this partial derivative notation means. And then this del notation, this gradient note, this means gradient, and you'll hear gradients talked about a lot. You probably already heard about them. You probably already know how to train machine learning models with stochastic gradient descent. And here we're going to learn the mathematical underpinnings of how that works. You don't have to understand the mathematics to be able to train the models at all. That's what Jeremy's done with his FastAI courses. But it's nice to learn the mathematical underpinnings as well, and that's what we're here to do. So what is a gradient? A gradient is just a nice way to organize the derivative of a multivariable scalar function. So you basically create a vector, and the first element of the vector is the partial with respect to the first variable, and the second element of the vector is the partial with respect to the second variable. And you'll see right away that this is extensible to functions of many, many, many variables, you know, not just functions of x and y, because that's what a neural network is. It's a function of many, many variables, which are the weights, and also the function is that we're going to be dealing with in neural networks is more complicated than just a scalar function. We have to deal with vector functions. And so we need a way to extend this gradient concept to vector functions. And what is a vector function? Well, it's a function that has components, that has, you know, like it could have, if you just think about it in 2 dimensions, you could have a function that has a component it could have 2 components. You know, it could have a component of one variable, and it can have a component of another along another axis. So, so you know, you could have a function that has it's a certain function of x and y, but it's a vector along the x direction for that function, and then it's another vector function of function of x and y along the y-axis. So that would be a simple 2-dimensional example of a vector function. Okay, so so the idea in section 4, which is really the body of this paper, and you'll notice that it covers most of the paper, is matrix calculus. We're basically learning how to work with gradients of vector functions, and to do this, they introduce this thing called the Jacobian, and it's abbreviated by J. But what it is it's again a notation to handle vector functions of more than one variable. So here we have a vector function, which is the gradient of f of x and y. It has 2 parts to this function, the gradient of f of x and y and the gradient of another function g of x and y. So, and you can imagine that it could be extended further in this direction by stacking up more functions, you know, more gradients of more functions. So it becomes a 2-dimensional object instead of a 1-dimensional object. But the rows are these same 1-dimensional objects that we just studied in section 3. They're just gradients of functions. So each row now becomes a gradient of a function. Okay, and they give you an example here where, you know, they specify, okay, for this example, f of x and y is 3x squared y, like in the last example. And then we're going to introduce another function, g of x and y, which is 2x plus y to the 8th. That's just a simple So that's a simple vector function in 2 dimensions. And this shows you how to construct the Jacobian. So the rest of this section is going to be, now let's extend this to many dimensional vectors and many dimensional functions. So you're basically going to extend this in the x direction, and you're going to extend it in the y direction and make bigger and a big, giant 2-dimensional matrix. But again, a Jacobian is nothing more than a way to organize a bunch of gradients. Okay, and it just organizes them in this nice way. Let's see. In this paper and in a lot of the work that you will see if you try to read the literature, they use the numerator layout, which means that the dimensions of the vector space go to the right, and the dimensions in the function, the different components of the functions go vertically. There's also the denominator layout, which is basically this thing transposed, so that the rows become the coordinates, the coordinates of the function, and the columns become the different functions stacked up. So it's, again, just another way to do it. Okay, it's just notation. So you get familiar with the numerator layout, and then if you have to read a paper that involves a denominator layout, you can translate to yourself. It's just the transpose, the matrix transpose. Okay, so this is the part where they generalize the Jacobian to many dimensions and many different functions, and it looks very similar to what you saw. It's just that it's got more. It's got a higher dimension, a higher number of rows and columns. Okay. This we'll be reading through. I'm not going to go through that in any more detail. The one thing I do want to point out is they've introduced this notation, and what this is, so this is something new for you maybe, but they define what they mean here. The circle symbol in this paper represents any element-wise operator. So it could be addition, or it could be subtraction, or it could be multiplication. And what it means when you take FG, it means to multiply, or say if you have an x inside, that means multiply the elements element-wise. If you have a plus inside, it means add the elements element-wise. If you have a minus inside, it means subtract element-wise. So it's just notation, and it's nothing to be intimidated by. Just get the definition straight, and then you'll be able to interpret it when you see it. So let's push on here. We'll be reading this time and next time, all of section 4. That's really the main part of it. But let me back up to the top. The goal of this is all to understand how neural networks work. In other words, what happens under the hood when you're training a neural network. That's our goal. And remember that it all has something to do with the loss function, right? It all starts with the loss function. We compute the loss function, and then we do back propagation by computing a chain of derivatives starting with the loss function. We're differentiating the loss function by the weight vectors. And that's how we calculate the updates. That's how we calculate the updates to the weights. So that's where it all comes back to. So let's keep that in mind, that is our goal, to understand the underpinnings of how neural networks get trained. So in order to do that, we have to slug through this theory section, this section 4, which is very long. It's all the theory. But now we get to the application part. 5 is sort of the first level of application. We learn how to apply the gradient to a neuron activation, to the output of a neural network, which is an activation function. So let's look here. He draws us a nice little diagram. This is sort of what a neural network, what a node of a neural network looks like. You have inputs, you have weights. You're going to multiply the inputs by the weight matrices, and then you're going to add the results, and then you're going to add a bias, which is another vector, and then you're going to apply the activation function, and then that's what comes out. Now, so the idea is when you're doing back propagation, you're going to be that's going to involve gradients of activations. So that's one of the pieces. That's one of the pieces to understanding how neural networks, the mathematics of how neural networks get trained. So then section 5 is that piece, covers that piece. You can see how they're systematically building up all the pieces they need to understand neural networks. So now let's slog through this whole section, which we're going to do partly today. Get to section 5, which is the piece that I just told you about, differentiating activation functions. And then, oh man, this is long. Okay, there we go. So this is going to be the piece of how to apply gradients to activation functions. And then finally, the meat is the section 6, where we learn how to take the gradient of the loss function. And that is the key piece to understand, is how the weights get updated, which means, and that's what it means to train a neural network, is to iteratively update the weights until you get, until you've trained the network to give you the output that you want. Okay. Now, finally, section 7 says where to go next. It's a basic short summary, but it says where to go next, and he gives you some really nice references. This one, I found this one was really great. So we've learned how to differentiate. So in this paper, we will learn how to differentiate. We'll learn how to extend our concepts of scalar differentiation to being able to differentiate vectors and to be able to differentiate vectors with respect to vectors. But the next step is to learn how to differentiate vectors with respect to matrices, and also matrices with respect to matrices. So again, you can imagine it's a lot of notation to learn, and they give you this reference, which I found is really excellent. Let me open it up for a sec. This is a paper that's written by this engineering professor, but it's very short, and it goes through it. It basically goes. It takes up where Jeremy's paper left off. So that would be the place to go next. And I think he did a good thing here. He started introducing the notation at the beginning, where Jeremy's paper, they introduced notation at the end. And I think it's worthwhile for us to look at the notation at the beginning. So let's see, here's, let's start with, so the way I would start this paper before you guys start reading is I want to go through section 9 with you first. Let's just make sure that we're all on the same page about this. And then I'm going to back up and go through section 8 a little bit, and then I'll turn you loose to do your reading. Okay, so to be all on the same page, we have to understand the notation. Notation is like a language, and I have this quote that I really like. I want to show you. It's from Galileo, one of my favorite persons. Here we go. So Galileo has this idea. He said the universe cannot be read until we have learned the language and become familiar with the characters in which it is written. It is written in mathematical language, and the letters are triangles, circles, and other geometrical figures, without which means it is humanly impossible to comprehend a single word. So, you know, that's nature. Mathematics has progressed a lot since Galileo, and neural networks, the language of neural networks, isn't triangles, circles, and other geometrical figures. It's derivatives and gradients and vectors and loss functions, that sort of things. So we have to become familiar with all the notation that's involved to understand those things. And so that's the place where we should start before we start reading this paper. So now let's go back to the paper. Let's see, now I want to share here. Yeah, so let's just go through this section quickly. So lowercase letters in bold font, such as X with a bold X, that's a vector. And all those in italics, like X italic, those are scalars. And when there's the subscript on an italic X, that means a component. That means, sorry, the ith element, sorry, when there's a subscript XI, that means the italic means that it's a scalar, and the little subscript I means that it's the ith component of the capital X vector. So, you know, you're used to, maybe in your calculus classes, you've talked about functions of X and Y, you know, f of X and Y, but now we're going to sort of abandon that a little bit, and instead of talking about the X component and the Y component, we're going to talk about because we're working in very high dimensional spaces. Some of these vectors that we're dealing with could have hundreds, thousands, or even hundreds of thousands of dimensions. And so instead of talking about the X component and the Y component and the Z component, we're going to talk about the X1 component, the X2 component, the X3 component, et cetera, et cetera. And you can see that that's a much more flexible way to think about components because it's extensible to an infinite number of directions, right? You can have as many dimensions as you want, and this notation will suffice to talk about that kind of a vector. So you could talk about the 999,000th component of a vector, and this notation suffices. Okay, and then when you see absolute value of X, it means the length of a vector X. But I caution you because sometimes you'll see these absolute value brackets and they might mean the cardinality of something. It might mean the number of elements in some set. So we got to be a little careful about that. You'll see that in this paper. Sometimes they use absolute value brackets to mean what you're familiar with from your algebra classes. It means the length of the vector. But sometimes absolute value might mean the cardinality or the count, the number of elements in a set. So just be aware of that. Okay, whenever you see an exponent t, that's the notation that means the transpose of the vector. What is the transpose of a vector? Well, when we talk about vectors, almost always in neural networks, we mean a vertically arranged vector. So it's arranged from top to bottom like that. So a one-dimensional vector would be something that's organized vertically, right? So what is the transpose of a vector? It just means to flip it and organize it horizontally, to organize all the elements of the vector horizontally. So in this paper and in most of the literature, when you say a vector X, you almost always mean a vertically arranged vector X. And so the transpose almost always then means that vector arranged horizontally. And that's a little different from what you're used to in your math classes, because as I remember in my math classes in high school or whatever, they always arranged vectors horizontally. So you'll just have to get used to thinking of vectors arranged vertically. And the reason is that that's the way computer languages think of vectors. All right, what about this weird notation here, sigma? It's a Greek letter, capital Greek letter sigma. And in mathematics, and then it has lower and upper symbols on it. I equals A to B. So this means, the summation from I equals A to B of xi. So it just means, the way they explain it is a for loop that just iterates from I equals A to I equals B and sums all the values. So you should be familiar with that from your high school classes, or it's not intimidating. It is a Greek symbol, and all it means is sum up all the elements of the vector vector x. Sorry. F of x refers to a function called x with an argument of x. Everybody knows that one. I means a square identity matrix. So all that is you know, it depends on what dimension you're talking about. If it's the x, if it's a 5-dimensional space you're talking about, that means that it's a 5x5 matrix with ones along the diagonal. So that's what a 5x5 identity matrix would be. A 2x2 identity matrix would be you know, a 2x2 matrix with the diagonals of 1. Okay, and then diag x, this is basically a function you'll find in every computer language. You specify some vector, and it will construct a matrix whose diagonal elements are taken from the vector. So that's what that means. Okay, and then we come to the dot product of two vectors, which is the summation of the element-wise multiplication of the elements. So you can imagine two vectors, w and x. They both have the same dimension. Let's say they're 3-dimensional vectors, right? Then what does this mean? N is 3, so we're going to sum from I equals 1 to 3 of wi xi. So that means w1 x1 plus w2 x2 plus w3 x3. And here's an example of that notation that they introduced, where you have a circle with in this case, a cross in it. that means element by element multiplication, because the sign inside the circle is the multiplication sign. So that means element by element multiplication of these two vectors. And another way to express this is W transpose X. But I think there's an error here. This should be a bolded W to denote the vector W, and then this should be a bolded X. So if you think about this, two vectors that have the same dimension, and the transpose mean arrange the first one horizontally and arrange the second one vertically, because the default is to arrange it vertically, right? So W transpose times X, again, this should be a bold, if you're taking notes, this should be a bold W, and this should be a bold X by their own definitions. So this means arrange the vector W horizontally, arrange the vector X vertically, and then take the product, the vector product, and that will give you the same result as the dot product. Okay. Any questions up to here? Because I know I've talked a lot.
Yeah, I wonder whether the W transpose X is written that way because it's not really like a proper matrix multiplication, because if you did do it, a vector and its transpose multiplied, you'd get a square matrix.
No, you wouldn't. Not if you arrange this vector horizontally. You're right. If this was a vertical vector and this was a horizontal vector, then you would get a square matrix if you perform proper matrix multiplication. But if you arrange if you arrange this as a transpose, it means arrange it horizontally, and then X is arranged vertically. And if you do that matrix multiplication and follow the rules that you know of for matrix multiplication, you will get a scalar.
Oh yes, you're quite right.
Yeah, most of the W is written in small letter, and if it is vectors, the previous one, they are written in capital, like X and W.
Yes, so by their own definition of what a vector should be, you always write a vector in bold. So
yeah, and capital letter.
That's correct. Well, not capital. It's not capital. See, that's the small letter right there.
Okay.
A capital letter would mean a big W. Okay.
Okay.
But yeah. Okay. Any other questions? Okay, great. So let's just go on. I want to get through this so you can start reading. Differentiation. The thing you might not have learned in school about differentiation is that it's interesting to consider it as an operator. That means as something that you can apply to a function. In other words, this thing by itself has a meaning. A lot of times in your math classes, you only see df dx or dy dx or dz dx as a, kind of like, looks like a fraction, right? But it's nice to think about differentiation as an operator that can be applied to a function, or that maps a function to another function. And so when you think of it in that way, if you say apply d by dx, apply this operator d by dx to f of x, that's the same as so here it is, apply d by dx to f of x. That's the same as df dx that you would normally associate with, right? And again, if y equals f of x, then you could apply d by dx to y, and then you get dy dx. It doesn't seem useful now, maybe, but it might be useful in the future. You can also think of the partial derivative as an operator as well. In other words, the partial d by dx without any of this stuff, it has meaning all by itself. It just means take the derivative of whatever comes next, of whatever comes after me, take this derivative with respect to x. Okay, and then the gradient also can be considered as an operator all by itself. This nabla, it's a Greek letter nabla. If you consider it all by itself, it has that meaning. It has the meaning of take the gradient of whatever comes next to me on the right. Okay, the Jacobian, as we already mentioned, arranges the gradients vertically when we're doing numerator notation. If we were doing denominator notation, it would be the transpose. But for now, in this paper, we'll just have to worry about numerator notation. And then finally, this notation where you have y equals, and then you have this bracket, and then you split into two conditions. It's just a way of saying that y has one value, has a value a if condition 1 is true, and it has a value b if condition 2 is true. You might remember this in association with the ReLU activation function, because the ReLU says take 0 if x is, ReLU of x is 0 if x is less than or equal to 0, and ReLU of x is x if x is greater than or equal to 0. So that's the application. That's one application of this notation. If you could use it to define the ReLU function. Okay, that's all I want to say. I know I've taken a lot of your time, but I want to get you back to the reading, and we'll, I guess, we'll read until 11:30 because I talked too much, and I want to spend more time reading, and we'll still have a half an hour at the end. We'll start discussing at 11:30. So any questions before we get started? Yeah, the chat asked a question. How do you call this letter? It's called nabla, the Greek letter nabla. Okay.
Is there a limit to which section we are going to read up to?
Yes. As I mentioned, we're going to be reading up to page. Let's try to get up to page 14. Or let's get up to page 13. I think that's what I set for the goal, right? Yes. Up to, in other words, up through section 4.4. That's our goal for today. Okay. So we'll get together. We'll just silently read now, and we'll get together at 11:30 for discussion. Here we go.
was easier to get it.
Okay, so I hope you've had a chance to read at least most of that section. If you haven't, don't worry. You can, you can catch up later. But anyway, now it's time to have a little discussion. And so the best thing is if you had some questions, anybody that had questions on this could lead off, and then let's just throw it open to the community. I don't have to be the only one to answer the questions. Anyone that feels like they know can pipe in, can pipe up. So yeah, so anybody want to ask a question?
So I wanted to ask a general question. So is the reason that we're using the simplified Jacobians with the diagonals being defined and not zero everywhere else, because all of our inputs are orthogonal? We're assuming that because of that assumption that in neural networks that this is the calculations we would use. We wouldn't need to worry about Jacobians with non-zero values on off the diagonal.
Yeah, so I think he's trying to give us a general view of Jacobians, but then he's specializing it to the particular kinds of calculations we're going to see when we do calculations with neural networks. Yeah. And I realized I jumped in. I shouldn't have done that. I should have let somebody else answer it. So another question.
Sorry, go ahead.
I still sort of don't understand why would every Jacobian be a square matrix? Essentially, it need not be right. I may actually have m functions and n attributes of the variables that would actually give me an m by n matrix, if I'm not wrong.
This is my question.
Yeah.
Sorry?
This is my question as well. Does the Jacobian always have to be a square matrix?
Someone want to answer?
I don't think so.
So the Jacobian is a generalized concept, and it's basically if you have a bunch of different functions and you want to keep track of their derivatives with respect to a bunch of, so you have a bunch of functions of many variables. They're all f, g, h, whatever. There are a bunch of functions. They're all functions of the same set of variables x1 through xn, and you want to keep track of the derivatives. The gradient just gives you a way to do that. So it's
square.
No, I understand that but my question is like, why should it be the square matrix all the time?
It's not the square matrix all the time. It's the square matrix in the specialized calculations that we're doing for neural networks, and that's because each input to a neural network, each input to, let's go back to this thing here, each of the inputs to the neural network has a corresponding weight. So the W's and the X's are they're the same. They have the same number of elements in them, right? And so, in this special case that we're keeping track of the derivatives of some function of W with respect to X, let's say, then it's going to be square. But you're right to notice that it doesn't have to be square in the general case, but in the particular applications that we're developing here, it's going to be applied to training a neural network, and so it reduces to a square. And also the functions involved are reduced to simple functions, like functions of W times Z or X times Z or W dot Z. They're not the most general kind of functions that you could have.
And I guess that's where the diagonal bit comes in, because we're assuming x1 times w1, x2 times w2, xn times wn.
Mm-hmm.
That you don't multiply x1 by w2. It doesn't do that kind of calculation. It's only the kind of like the diagonal entries that are done.
That's right.
Isn't it the case that on page 8, when he actually shows the various shapes, that the general shape of the vector to vector can be a rectangle, doesn't have to be a square? He unfortunately quickly takes it to the identity and says that it's a square since m is equal to n. But
Right, this is the general
have to
idea.
be, as several people have pointed out, when he just shows the shapes and in the middle of page 8, the bottom right can be page 8, just the shapes of vector to vector right there. So that shape on the right can be an m by n rectangle.
Yeah, that's correct. So if you look at this, this is the general. Oh, all of a sudden I've developed an echo. Oh well. All right, so this is the general expression for Jacobian. You can have, m rows and n columns. So in general, it is a rectangular matrix. Okay, and then what Srinivas is saying, I think he was bemoaning the fact that that this looks square. It doesn't necessarily have to be square. It should be, we should be able to include a rectangle. This should be a rectangle, is what Srinivas is saying.
Yeah, in the general case, it's a rectangle, and then immediately below he says the Jacobian of an identity function where m is equal to n, and then that's a square. But that's
that's how that's how I'm understanding it as well. Is that the square is enforced by the identity matrix, because you can't have an identity matrix if it's not square, because you can't have a diagonal of ones. At least that's how I understand it, but I may be wrong on that.
No, you're right. And the general case is a rectangle.
Can I say something? In this case, as pointed out, it becomes square matrix almost inevitably, because most functions are multiplication of w and x. So the dimensions of w are the same as dimensions of x. And that is one of the main reasons why it actually becomes square matrix.
Right, that explanation is on the bottom of page 7. So if you scroll back to page 7, to that last section of page 7, he states it right there. Go up just a little bit more, please, Joseph. Right there. So that sentence where it says it's very often the case that m equals n, and it's because of what folks are saying right now. It's because you have a scalar function, and every time that you have an input, you have a weight. If you don't have an input, you're not going to have a weight, or it's going to go to 0. So m is equal to n when we're dealing with neural networks.
Right. So if you were a theoretician and you wanted to just develop this as a theoretical concept, then you would realize that it's a rectangular matrix. But now he's specializing to the case of neural networks, and his first application shows you right away that we're being driven to diagonal entries, because he's taking the Jacobian of x. I think it's on this page. Yeah, right here. He says, let's suppose we're going to take the Jacobian of the identity function f of x equals x. Well, what is this f of x? It has x. It has n elements going this way, and you're going to be taking derivatives with respect to each of those n elements, and so m itself is also going to be equal to n, and so that's what he's developing here, showing you that it becomes diagonal. Okay, since m equals n. Okay. Yeah, so this is the first development where he shows where he actually does this a differentiation of a vector by another vector, and he shows that is the identity matrix in this case. And just look at it again. The thing you're taking the derivative with respect to, that determines the number of columns. Okay, so x is a vector that has n elements, x1 through xn, and you're going to need one column for differentiating by each one of those x components, right? Now, what determines the number of rows? The number of rows is determined by the by the dimensionality of y, and y is the remember, y is basically a stack of functions. But in this case, y is the same as x, because we're trying to take the derivative of x with respect to x, right? We're taking the derivative of y with respect to x, but y is itself equal to x. So the number of columns and the number of columns, which is determined by the denominator, is the same as the number of rows, which is determined by the numerator. Does that make sense?
Yes,
Yeah,
but,
sure, that
but
makes
that's why,
sense.
Joseph, I'm saying that if
That makes sense.
Yes, but then my point is it has, at least to this point, nothing to do with neural networks, right? Basically, you could choose a different function which would then have m different than n, and then in the general case, m and n don't have to be equal.
Of course, but
Yeah.
we're specializing to the case of y equals x. So that's the point of this whole thing. We're specializing to the case y equals x, and then he shows that, yes, in this case, you end up with a diagonal.
So this is not generalized Jacobian. This is just specialized in our case of neural network, right?
No, what we showed here on page 7, this is the generalized Jacobian.
Yeah, sure.
Okay?
Yeah.
And now we're specializing to the case of, let's take derivatives with the derivative of x of a vector x with respect to itself. That's our first example
where
of vector
x, where y
differentiation.
is equal to vector y is equal to vector x, right?
Yes. So this is a special case. It's our first calculation involving vector differentiation of a vector with respect to a vector. And we see that because we've chosen y to be the same as x, that gives us a diagonal result. I mean, sorry, a diagonal matrix as a result.
So
and it's a square.
So in the future, I mean, I haven't read the later part of the paper. So we are going to continue with this specialized part. We're going to drop the generalized Jacobian. We should always in the future, m is equals to n.
Well, let's open our minds. I think in the computations we're going to do, that's going to be the case. But don't forget that it could be rectangular. And I won't say for sure that you're never going to have to deal with rectangular matrices in neural networks, because that's not true. So just keep in mind that there is this general form, and but we're specializing to we're specializing this for a certain kind of calculation, which is training neural networks. And for this application, we're mostly going to be dealing with, in fact, I think we're always going to be dealing with square Jacobians in this paper.
Does this map to the weight matrix in neural networks, or is that going too far, Joseph?
No, it is. I mean, the weights, the W's that we're talking about, the reason why he introduces them later on, he introduces these mysterious variables called W. Well, because it's just convenient, because we're going to be seeing those are the weights. You know, yes, somewhere down the line, he starts talking about W's.
So this Jacobian matrix is the weight, is the matrix of gradients that we'll be updating.
Well, this is one of the pieces that might be involved in computing that matrix. So he's systematically computing all the pieces that we're going to need, and then he'll put them together in sections 5 and 6 to show how it comes into training neural networks.
Another option, another alternative, I just want to point out, even if we had more than one function of x, say we had 5 functions of x instead of one function of x, we could have 5 different square matrices.
No, I don't think, if you can actually scroll down, he actually quotes an example of using more than one function. I don't think we would have 5 different square matrices.
No.
I have a question on page 8, first paragraph. Why is the horizontal n vector, the length of the vector n, equal to the n parameters as well? Okay,
that's the definition of the gradient, right? We talked about the derivative of a scalar function with respect to a vector. That's what we're doing here. We've got a scalar function fi of x, which is some component of this bunch of functions. It's let's say it's the ith component. it maps a vector into it. The function f sub I maps this vector into a scalar, right? So this thing here is a scalar. And what we're doing is we're taking the derivative of a scalar with respect to a vector. And he's shown us how to do that. It's basically just this notation back in section 3. The derivative of a scalar function is just, you know, with respect to its component, with respect to the vector, with respect to the vector x. In this case, it's the vector x is has components x and y. But this is the definition of the gradient for a scalar function. And what it does is it maps the scalar function into a vector that has the same number of components as the vector that you're differentiating with respect to. So in this case, we're differentiating with respect to x and the vector x comma y. That's a two-dimensional vector. So it has two components laid out along the horizontal direction. That's a definition, the definition of the gradient. Okay, does that make sense, Wencheng?
Yeah, so you're saying basically there's two items right now in that vector, and we have two variables.
Well, those two items are, yeah, those two items in the vector, yeah. Well, the two items in the vector are the variables, and right. Well, and the two items in this resulting vector are the derivatives with the partial derivatives with respect to the first and second of the two variables.
Gotcha. Okay.
Okay. So to keep this in mind, the derivative of a scalar with respect to a vector, that's a gradient, and it's a horizontally laid out vector that has the same number of components as the vector that you're differentiating with respect to. That's just the definition for notation. Okay, so going back to your question, yeah, hold on for a sec. Going back to the question which was on section 8, page 8, where this is the question that Wencheng asked. He said, the claim is that each component here is a horizontal n vector because the partial derivative is with respect to the vector x, which has n components. That's exactly what we just went through, right? Except this is a case where n is bigger than 2.
And that's why remembering this picture that Joseph is just sharing is important as we move forward, because that picture summarizes essentially what you've been seeing in a lot of mathematical notation. A scalar by scalar is just a scalar differentiation, but the scalar differentiated with respect to a vector is a horizontal vector with as many parameters as x has, and therefore that corresponds to the length of x.
Yeah, this is a really nice drawing that encapsulates all that, right? I mean, right. The derivative of a scalar with scalar is a scalar. The right. Derivative of a scalar with a vector is a horizontal vector. The derivative of a
vector with respect to a scalar first.
Well, the derivative of a scalar. Let's see, how do we do this?
The
vector with respect to a scalar is a vertically laid out vector, right? Because this vector itself is vertical, and then when we take the derivative with a scalar, we're just taking the derivative of each piece of it, of each component, and we're laying it out, and it remains a vertical vector. Okay, so the surprising one is this one, really. You know, this is the sort of the unfamiliar one, that the derivative of a scalar with respect to a vector should be a horizontally laid out vector, and then the derivative of a vector, of a vertical vector of functions by a vector is going to be this in general rectangular matrix with m rows, the m being the dimensionality of this vector, and n columns, n being the dimensionality of x. So in general, as Srinivas points out, this should have been shown as a rectangular vector, but in our case, in our application, it's usually going to be square. So you will get a square matrix in a general case.
Is there a hidden transpose? Yeah. Is there a transpose being used behind the scenes here somewhere that's allowing that, allowing the
No, there's no transposes. This is what's called the numerator layout, and there's no hidden transposes. A vector is always defined as vertical. You can see, right? And so this is a transpose. This is a transpose of a vertical vector, right?
Okay. So
just can you scroll back to page 6?
Sure. Where are we?
Yeah, right there, right above matrix calculus.
Okay.
Yeah, that paragraph which says, so the gradient of f of x, y is simply a vector of its partials. That makes sense.
Yes.
The next line, gradients are part of the vector calculus world, which deals with functions that map n scalar parameters to a single scalar. What does that mean?
Oh, that's kind of strange.
That's not accurate, Rakel, because that he is only, and again, I may misspeak with respect to terminology in math, but obviously as he shows vector, scalar, or scalar vector differentiations, then it doesn't result in a single scalar.
Right, okay.
I think what they mean is that each of the n scalar parameters gets mapped to a thing. So, well, no, it doesn't. No, it doesn't work that way.
Yeah, even
if you have, even a scalar function, when you differentiate with respect to a vector, it becomes a vector, a horizontal vector. So that's a good point, Rakel. This is not correct. You should take a note if you're making notes. So boom, like that. All right. Next question.
The general derivative, right? Like say you have a function of x, so f of x. So the derivative with respect to x has a meaning, right? Like it has an intuitive meaning. Like how does the function change as x changes? So with this Jacobian matrix, is this just like a logistic? So we keep track of everything, or does that?
I see what your question is. Like I'm going to let somebody else try to answer it though. Anybody? I think what
I think it's the exact same thing. It's just that with respect to each parameter, he mentions like how you're wiggling with respect to each of the xi's in the vector x, right?
Right. I think Mahul's question is actually what's the geometric interpretation of this case of the derivative of a scalar function with respect to a vector? What is the geometrical interpretation of it?
Yeah, or maybe just like if that Jacobian matrix, does it, it's like.
So if you look at one element of the Jacobian matrix, it's exactly what you're defining.
Right. But,
it's almost like Mehul, it's almost, in fact, it's keeping all the other parameters just one parameter, keeping all the other functions constant, just one function.
But Mehul is correct in pointing out that there is a geometrical interpretation. Each row of that matrix is showing you the direction in which the function is changing with respect to that parameter. So it's more than just, as Mehul pointed out, it's more than just an organization. It turns out that organization of the vector, of the partial derivatives into a vector, has a really nice geometric interpretation, and it tells us the direction in which that function is changing. It's the tangent to that function with respect to the vector x.
That's each row, and each column also has an interpretation, right? For the Jacobian.
Graphs for loss functions that you kind of just descend the fastest when you do such calculations along the gradients.
Right. So each row is showing you the direction in which that function is changing with respect to remember, the derivative of a loss function is a scalar. The loss function is a scalar function, right? And so it is this case. It is this case that Rakel was pointing out. It's the derivative of a scalar function with respect to a vector. Let's go back down to section 8 where it's more general, where it gives a more general statement of that. So you can think of, so thinking ahead, think of the loss function as the scalar function that we want to differentiate with respect to a vector x. Where are we? Where's that thing? Where's that? Somebody remember what page? I think, here we go. So this is our, this is what we should be thinking about, this row here. So the fi, think of this fi of x as our loss function, right? And so the derivative with respect to x, as we were saying, is a row vector. And that row vector is called the gradient of the loss function with respect to the vector x. And so that gradient tells us the direction in which that function is changing. That's what it tells you geometrically. And each of its components tells you the direction in which the function is changing with respect to that particular component. So let's think of this gradient as an n element, as an n component horizontal vector. Let's make it concrete. Suppose we have four directions. We're working in a space of 4 dimensions. So the gradient has 4 components, and the first component of the gradient tells you the direction in which the function is changing with respect to x1, and the second element in this row vector tells you the direction in which the function, well, not the direction, but the magnitude in which of the change of the function with respect to x2, and so on. So the geometrical interpretation of this vector as a whole, it says, if you want to get to the minimum of the function, go in the negative direction of the gradient. So that's the picture you have in your mind of this loss function landscape where where it's going down to a minimum, right? That's what we always want to do in neural networks. We want to get to the minimum of this loss function. Well, the gradient is the key thing, because because if you know the gradient, then you know the direction. Then you know that opposite to the direction of the gradient is the direction in which this function is decreasing, and you're always trying to minimize the function. So it basically says, if you want to minimize the function, always go in the direction opposite to the gradient. And we've just learned how to compute gradients. So that's a key component in learning how to update the vectors, right? You start with the loss function, the derivative with respect to some parameters that you're interested in adjusting. You're taking the derivative of the loss function with respect to some vector of parameters. And you want to know how to update those parameters. And the starting point is to calculate the gradient. And then you multiply it by -1 times some learning rate. And that gives you the amount that you want to adjust to the parameters. So that's where it's all going to come in section 6.
I think, is it correct to imagine each of those gradients as each of those 4 that you describe as leaving the origin, and the angle in comparison to each of those lines to the origin is an interpretation of the gradient. So as the angle increases, the gradient also increases. So you're trying to minimize that line for each of those four gradients.
Well, maybe it's better to think of the gradient as a tangent. So you can think of this, you can think of this loss function as, it's easy to think about this in 2 dimensions, right? Because we have 3 dimensions to think about, right? And the z direction will be the loss function, the magnitude of the loss function, right? And the x and y direction would be 2 parameters, right? So we can visualize this if we have a simple case where there's just 2 dimensions, 2 parameters. So it's always useful to do this, to think about a 2-dimensional function as our easiest example, right? So let's suppose we have a function of x and y, and then we have a loss function, which is some 3-dimensional shape that, it's a 3-dimensional shape, the loss function. And what we want, the gradient is basically a tangent, is always tangent to this shape. So you can think of the shape as maybe in a nice case, you can think of the shape would be like a paraboloid or something, very simple shape.
Just sharing a link with you so we can actually look at a figure and then you can point out.
Okay, super, thank you. Yeah, there we go. This is beautiful. So yeah, here's an example of the shape like that we were thinking of, some kind of a very simple.
Sharing that screen though.
Oh, I'm sorry. I thought it was. Okay, let me stop. Oh, that's right, because I'm sharing a PDF document. I need to share the browser. Thank you. So this is great. Okay, so now I think you can see right where we're looking at.
Yep.
You see it? Okay, let's look at one of the simple, but look at all these very complicated looking loss functions. And that's one thing to realize, is that loss functions can get really nasty, right? They can have all kinds of wrinkles and kinks in them, and that makes it difficult. That can make it very difficult to get to the minimum. But when you have something like this is like the best you could get, right? Sorry, I want to get this. What happened? I want that figure. Let's see.
I think it must be there somewhere down on the page.
Yeah, there's a link to it. Is this it? No, related images. How about if I just open the image? Open, view image. Yeah, there we go. So yeah, so this is it's a two-dimensional surface that's embedded in a three-dimensional space, right? It's like a sheet, and so this is, so the z direction, I don't know if you're used to seeing three-dimensional plots, but the XY plane is the bottom plane here. That's what you're used to in your regular, in the math classes that you've taken in high school. But in 3 dimensions, you can also have a z direction, right? And the z direction, you can think of that as the magnitude of the loss function. Because remember, the loss function is a scalar. So imagine this loss function in 3 dimensions, and it's a sheet with that's held, so that you can get to the minimum of it, right? And you can roll a ball down to the bottom. And if you release a ball, gravity will make it find the bottom. And so, minimizing a loss function is kind of like minimizing the energy in a system. That's minimizing the potential energy in a system. There's a paper that was just published on that, but let's get back to what we're looking at. So the idea is you take the gradient of, this is back to what Mehul said, and I think that was a really super contribution that when he raised this point, this convenience, this list of functions, this horizontal list of things that we defined as the gradient, this turns out to have a real geometrical interpretation, even though it was defined as a convenience. But we can actually make an interpretation of it, and the gradient is basically going to be tangent to the sheet. The gradient of this function, the gradient of the loss function at any point is going to be a vector that's tangent to that loss function. And that vector will be the one that we calculated using our simple definition, all right? And the idea is, so for example, the gradient here, it will point this way. The gradient generally points towards the direction of increase of the function. And so for our application, we're trying to minimize the function. And that's why I say that we want to proceed in the opposite direction of the gradient. The gradient points here, the gradient points up. If we want to get to the minimum of the function, we need to travel down, right? And the gradient isn't the end of the story. You have to multiply it by something called the learning rate, which is the multiplier. It says how much of the gradient to use. Do we want to use a high multiple of the gradient? Do we want to travel make very large steps down in the direction of the minimum, or do we want to make small steps? And you might think that, well, if we're up here, if we know that we're up here, at first we can take large steps. It'll be fine. But if we keep taking large steps, then as we get closer to the bottom, the steps are going to be too large, and we might end up bouncing around from side to side here, or in 3 dimensions, and we'll never get to the bottom. So eventually you want to be able to adjust the learning rate to make it smaller and smaller as you approach the minimum. And that's the way that it works when you train neural networks. You start with there's adaptive learning rates. You can start with a larger learning rate, but then as the gradient becomes closer and closer to 0, you take smaller and smaller learning steps, and you eventually get to the bottom. Yeah.
A key thing to kind of remember along with that is that as you keep going down, inherently you have like that annealing happening because your gradient keeps reducing. So like even if you did reduce your learning rate, the gradient actually is reducing, right? Because when you finally hit the bottom, the gradient is going to be 0.
Right. Yeah, but so that's a good point. The point is that that just was made is that the gradient as naturally gets smaller as you get closer to the minimum, because remember at the when you minimize a function, the gradient is 0, just like in one dimension, right? At the minimum of a function, remember the slope is 0. That's a one-dimensional analogy, but in 2 dimensions it's the same thing. The gradient is 0. So the gradient gets smaller and smaller as you approach the minimum. But still, if you start out with a high learning rate, a high multiple, you could end up bouncing around and not actually getting settling down at the minimum. So yeah, any other questions?
Page 9, I have a question.
Sure, let me go back to the document. Okay, here we are. You see the document again?
Yes, right
Okay.
about the section derivatives of vector element.
Derivatives of
yeah, right there. Just
derivatives of element wise, vector
Yeah.
element wise. Okay.
Yeah, right about that. The paragraph over there. Why does it say also be careful to track whether a matrix is vertical or horizontal?
Yeah.
What difference is that making there? I kind of missed something.
Anybody want to jump in?
I'm guessing that this has to do with whether or not it's numerator form or denominator form, because one of the points that he makes early is that software represents the Jacobians in the denominator form. So you're using transposes as opposed to column vectors. That's what I think.
Yeah. I mean, this is just a practical piece of advice. I know that it works, that it's a really good piece of advice. Whenever you're working through an expression that involves vectors and matrices, make sure that you know whether you're dealing with horizontal vectors, row vectors, or column vectors, because otherwise you could make a mistake. And as long as you know the dimensions of all your vectors and matrices, you can try to predict, you can sort of predict what the result should be. And if it's not, then you know you made a mistake somewhere. You use a row vector instead of a column vector, something like that. Because
so like you mentioned, Joseph, like the concept of vertical and horizontal, to me, at least I have been familiar with, like with respect to rows and column vectors. When a matrix comes into picture, what exactly is going on? It's the matrix is vertical or horizontal that he's kind of...
No, the matrix is always the way it is. And the rows of a matrix are horizontal vectors, and the columns of a matrix are vertical vectors. Oh, I see what you're saying. He did say matrix. Yeah, well, a vector is a special case of a matrix, and I think that's what he's really talking about. He's talking about a vector here. I believe that's what that word should be. Because when he talks about, that is not a thing. There is no such thing as a vertical matrix or a horizontal matrix. It's not a thing. So I think you've noticed an error. He should be saying a vector.
Talking about like when you take a matrix, because like we were talking, like in the matrix, if you kind of break it down, each function is actually just a row, right? It's kind of represented like that now.
Yeah, okay, so there would be cases where a matrix is a special way of representing a bunch of column vectors, right? You just stack them, right? Or it could be a special way of representing a bunch of row vectors, so you stack them on top of each other. Maybe that's the sense in which he means. In other words, if the matrix is representing row vectors or if the matrix is representing column vectors, that's the thing that you want to pay attention to.
Yeah, and as somebody who just spoke before mentioned, when you do it manually versus when you do it with TensorFlow or PyTorch and you start comparing, then you can get terribly confused because of what PyTorch and TensorFlow do, which is invert some of, or transpose, I should say, some of the matrices. So if you're doing manual work, then even in matrices, you have to be careful, just what you guys were discussing, which is in what ways it's stacked.
Yeah, right. And also,
could one of you just give me a concrete example? Like,
okay, so for example, if you think of a matrix, normally when you think of a matrix, say a multiplication, you multiply a matrix times a column vector. This is This is what you usually think of, right? You're going to take a matrix and you're going to multiply it on the right, on the left. You're going to multiply a column vector by a matrix that sits to its left. So let's say we have x1, x2, and x3. And let's keep with square matrices for now. But so you're going to have entries here: A11, A12. The first index is the row, and the second index is the column, and then A13. And I won't write the rest of them because it's just you fill it in, right? There's 3 more here. This would be let's see, A3, 1, and so on. And then the last one would be A33. Okay, so the idea is you're multiplying normally. This is the way you learned it in high school, right? You multiply a matrix on the left by a column vector, and then you end up with another, you end up with another column vector if it's 3 by 3. So you'll end up with some vector Z1, Z2, and Z3, right? But this is the point that that Srinivas was making, that TensorFlow and also PyTorch, they invert this. Instead of multiplying on the left, let's call this matrix A for a moment. And in general, when you denote a matrix by a capital letter in bold. That's the way you normally denote a matrix. The way they do it in TensorFlow is they'll take instead, and let me call this vector X, right? X, the vector that I represent by that column vector. So this is the expression for the equation AX. Sorry, this is a small x. That should be a small x, sorry. I think I can erase something. Let's see, clear, no.
You can just put an arrow on top of X.
Undo, yeah. Well, I mean, let's just assume in your mind that these are bold letters, right? That these are bold letters. So the bolded A is a matrix, and the bolded X is a column vector. So this equation that we wrote down, this matrix equation, is AX equals Z. Small z, sorry. I gotta clear that. Sorry for my clumsiness. Sorry. Undo, yeah. Now this is a Z. A small z. Okay. Now, what they do in PyTorch and TensorFlow instead, and this is really confusing and Jeremy does it in his class too, and he never explained it, but you sort of have to stare at his lecture notes really hard and then you figure it out. What they do is they take, instead, they take X transpose multiplied by A transpose equals Z transpose. And I'll tell you in a minute what this looks like, but I'll tell you the reason why they do it. It's not perverse. It's actually because in neural networks, it's nice to think about the neural network as a directed set of operations. So you start at the input on the left, and then you proceed by operating on that input with matrices to determine the outputs, right? So you start with X, you multiply it by the matrix A on the left, and then you keep multiplying, to get the output. You just keep multiplying it by the next matrix and the next matrix and the next matrix, and finally you get the output. So you think of neural networks as processing information from left to right, and so the information comes in first, then you operate it on it with a matrix, with a weight matrix, and then the result of that goes through the next node in the next node in the neural network, and then that means operating on it with another matrix. And so you end up with this string of matrix operations that then leads to the end. So that's a nice way of thinking about how neural networks work. What does this look like? Well, X transpose, as we said, if you take X is always by default a column vector. So it happens to X transpose, it's a row vector, right? So it's a row vector, and it looks like this. So it's X1, X2, sorry, this is slow. I wish Zoom had a better way to draw things, but they don't, so at least not now. All right, and then what happens here is I'm going to draw the let's fill this the rest of the way. And this is A22, A23, A21. Remember that I index is, it's Aij. To identify an element in a matrix, you go Aij, where I is the row and J is the column. So for the second row in the first column, it's A21. For the third row and the second column, it's A32, right? So there's our matrix A. And then if you write it as you write the transpose, well, the diagonal is unchanged, right? It's still going to be A11, A22, and A33. But then what happens when you take the transpose is you're switching these two elements, you're switching these two elements, and you're switching these two elements, right? You can imagine just sort of flipping the thing around its diagonal. And so I end up with A21 over here. And I end up with A31 up here where I used to have A13, right? So I know that some of you already know these things and are bored, but some people might not be bored. Some people might need to see this. So, and again, A13 gets moved down here. So this one should be A13, and then let's see, A12 gets thrown down here. So this becomes A12, and then finally, let's see here, we have A23 gets thrown down to here, to the bottom row, A23. So this is all just writing out the transpose. And it might look boring, but you should get familiar with doing stuff like this, right? And then A32 is here. So this is how you write the transpose of A. Now, you should be able to convince yourself that X transpose A transpose does indeed give you Z transpose, which is going to be this horizontal vector. Remember, we had Z1, Z2, and Z3 in a vertical vector. That was Z. But Z transpose is Z1, Z2, and Z3 arranged horizontally, right? So, okay. So you should be able to convince yourself that this gives you the same result. And this is how I would think of it, right? When you multiply a matrix times a vector, you're going to do row column, right? The first element is going to be the first row dot product with this column, and that's going to give you Z1. And the second row, the dot product of the second row with that column vector is going to give you Z2, and the dot product of row 3 with X is going to give you Z3. Well, when you multiply these two objects together, following the rules of matrix multiplication, you have to multiply this row by this column, dot product it, and that gives you Z1. And that's the same dot product that we calculated here. The next element, second element, Z2, is going to be this row, dot product with the second column, right? And the thing is that dot products are commutative. That means if I take X dot A, X dot this vector, it's the same as if I wrote this vector dot X, right? They commute. The order doesn't matter. So in this case, we're doing the row of A dotted with the dot product of the row of A with the column vector X. In this case, we're doing the dot product of the X vector with the same A vector. So it's just an order that's changed, but dot products are commutative, and that's why you get the same answer, right? You get the same answer. So this is one way of thinking about the multiplication of the weight matrix by the inputs. And this is another way that's more adapted, more suitable when you're working in neural nets. Does that make sense to everybody?
All right, and then actually if you look at your AX is equal to Z, if you apply a transpose on both sides, mathematically also AB transpose, AB the whole transpose is equal to actually B transpose.
Exactly.
Right.
Exactly. Thanks for pointing that out. It's a mathematical property of the transpose that if you take AX transpose, the product of AX transpose, this is proven in in classes when you first study matrix algebra. You can actually prove this, that to take the transpose is the same as, it's just mathematically equal to X transpose A transpose. In other words, you reverse the order when you take the transpose. And so that's all this is. This is just a special case of this rule that that Rekil just pointed out.
Yeah, the other way I try to think about it, or it still confuses me sometimes, is whether the input is in rows or the input is in columns, and it's important to be aware of that as you do neural network processing.
Absolutely, yes. Yeah, and when I took Jeremy's, I think his second course, the deep learning from the foundations, he does a bunch of derivations and on his Blackboard during the lectures, and then he published, and then he I think those are just in the videos. But then if you look at those things really carefully, this is what it boils down to. This is what he's doing. He has a weird notation, but that's hard to understand. But this is actually what he's doing. He's instead of thinking about it this way, which is the way I always used to think about it, he's thinking about it in reverse order. In other words, taking the input first and then multiplying it by the weight matrix. And it's just a different way of thinking about it.
And the first linear transform you try out in PyTorch throws you for a loop too, because of the internal transpose that they do. So.
Mm-hmm. Mm-hmm. Yeah.
So one more question going back to this. So we don't do the transpose, right? That is kind of taken care by PyTorch, because I don't remember, like when I do a matrix I don't do a transpose explicitly. Or am I missing something there?
Srinivas?
If you tried, I believe, a linear transform, I haven't tried it in a long time.
So let's say, for example, if you're just doing like that linear layer,
a single row linear transform, then you may be surprised. I haven't tried it in a while, but if you look at what actually PyTorch implements by opening up PyTorch and looking at like a linear transform of a vector, then you may see in it a transpose.
Okay, cool. Yeah, I'll check that out.
Yeah. So the main point is just. So the main point is
when
just,
you do an m by n and stuff, it kind of tends to, by the time you get to doing images and text and stuff, and using frameworks like FastAI and stuff, all that gets abstracted out for you. But if you go right down to the bare metal PyTorch and try a single vector times stuff, I remember being surprised by what I got, but it's been a while, so I'll have to go back and check.
Cool. Okay. Yeah.
Yeah. So the main point here is that there's two different ways to do these kind of calculations, and you should be aware of them. And they're equivalent.
Okay.
It's just that this one is, at first for me, it was very awkward to think about it this way, but I got used to it.
Right. Yeah. Exactly. And then there's jargon overload with X being kind of used as input, X kind of, when you write Y is equal to MX plus C, that's again, that kind of becomes messy over there.
Yeah, because like, X initially is the input, but then after you operate on it, after it, at the output of the first layer, then it becomes the input to the second layer. So at first, X is just the data, right? That's the data, that's the input to your neural network. But then, as it gets processed from left to right, it goes through the layers of the neural network, and then the output of the first layer becomes the input to the second layer. So again, they call it X sometimes, and you could get confused because you're thinking of X as your data matrix, but it's so you just have to be aware of that.
Right. Okay.
So any other questions?
Yeah, I just looked at the linear layer, and Y is X A transpose plus B, according to PyTorch linear definition.
It's A times X transpose?
No,
wait.
X times A transpose plus B.
And so B is a horizontal vector that way, and X must be a horizontal vector as well. Yeah. Yeah, because if you imagine trying to multiply from the left, if x is on the left, if it's a column vector, then it won't work. You can't multiply a column vector, a 3x1 column vector, by a 3x3 matrix, because the rules of matrix multiplication say that the number of columns in this vector has to be the same as the number of rows in this one. Yes?
Just sent you the link, so if you want to pull that up, then we can look at it.
Oh, sure. Okay, let's do that. Back to I have to share the.
Sorry.
That's okay. I'll share that link. Boom. Let's see. Here we go. I gotta see where you shared it. Is this is what you shared?
Yes.
Oh, great. Okay, super. All right. So they must be thinking of vectors as horizontal.
Yeah, we can look at that because input is going to be the x here, right? And you can look at the dimension. The shape is mentioned down there.
Okay.
Yeah,
right. You jumped across.
Yeah.
Oh, I jumped across. Sorry.
Yeah, it only works if it's horizontal.
Right there.
Yeah,
right.
Oh, sorry. Further up.
Further up.
The shape. Yeah, right there.
Yeah.
It can
only work if it's horizontal.
Yeah, because the rules. Remember, there's rules for multiplying matrices, and the number of rows in the second matrix has to be the same as the.
Right.
Sorry. Yeah, it has to be the same as the number of columns in the first matrix. So it has to be a row vector that multiplies on the left.
Okay.
I missed this part. Why is it better to set it up? This matches X A transpose matches a neural network setup. I missed that part.
Yeah, because you want to think of a neural network as let's see if I can draw something. Let's see, sorry. Okay, so there we go. So you want to think of a neural network as operating on a bunch of inputs, right? These are your inputs, and and then they're operating. They get multiplied by a bunch of weights, right? They get transformed into the outputs. It's going to go through this black box, this neural network, and then out comes this output that's operated on by the weights matrix and adding the bias vector, and then multiplying by and then taking the ReLU function. Remember how that works?
Mm-hmm.
And so this is your X, and a linear layer could be represented by a matrix of weights and a bias.
Okay, got it.
Sorry. Yeah, and so and then followed by a ReLU function, right? So you can imagine the way this works is you take an input. I mean, it's a nice way to imagine the operation of this thing is to take a horizontal X vector, operate on it, multiply it by this weight vector, a square weight vector, weight matrix, sorry, add a bias, a horizontal bias vector, right? So I'm imagining here that there's a horizontal vector here and that there's a horizontal vector here, right? And then take the whole thing and operate on it by a ReLU function.
Right. Okay.
Right, and then that becomes, and that ends up being another row vector, right? Because you're this produces a row vector. This produces the bias vector is a row vector of the same dimension. So when you add those together, you get a row vector. The ReLU is an element by element operation. So the output of that is another row vector, right? And then that goes into the next layer as the input, right? That's what I mean by, so this would be called, normally this would be called, I think they have a notation, they call it Z, the output of a layer. And then that becomes the input to the next layer. And then you just do the same thing, with the ReLU acting on, the results of, so this could be layer 1, bias 1, and this could be Z1. And then you put it into the next level. So this would be Z1 as the input, this horizontal vector, operated on by W2, and adding a bias vector, sorry, B2 2, you see. And then so you're going to have a chain. You can have, this allows you to think of a generalized neural network consisting of one layer after another until you get to the end. And that's why I believe that this is a nicer way to think about these matrix multiplications, because it allows you to think of a neural network as a chain of operations. And you can see that in the structure of PyTorch and in the structure of TensorFlow, that's what you do. You build a layer, and then you chain them together. You chain these layers together to get, and it makes it very easy to do that. But this is what's going on under the hood.
To me, it's also the fact that you think of the input you're feeding as m examples of each row being an element, being one input example, right? So in this, for example, unfortunately, they will get terribly confused by the choice of their term, but in this case, the number of inputs is n. So it's n by the number of example rows that you have.
Yeah, so the number of
that point, I just realized when we did version 2 of FastAI, when we flattened MNIST out, we had like capital N was like 60,000 examples going along the row, and each of them was flattened into like 784 columns.
Yeah.
Right.
So that's exactly what, that's what, now it all makes sense. Fine, yeah. Okay.
That's why now, unfortunately, horrible term overload, because here n is used for the number of rows.
Yes.
Whereas typically in what we've been reading until now, m is used to indicate number of rows, and small n is used to indicate the number of parameters. So keep that in mind, so that you confuse the heck out of it otherwise.
Yeah, and the other thing to keep in mind is these weight matrices don't have to be square.
Right.
They're going to be, they're going to in general be rectangular. The number of examples, they're going to be, the number of examples is usually huge compared to the number of parameters, right? So this is going to be a very long matrix, but it's going to be relatively shallow. It's not going to be very deep, because this direction is m for the number of weights. So, like you're going to build, sometimes, if you've seen these convolutional neural networks, and they have like 500 dimensions or whatever, but they have, so m is 500 for one of these transformations typically, or could be, but n is typically thousands. You end up having thousands of training examples. So, yeah.
Also, when we typically do mini batch, so it's not really just a row for the X, it's actually a matrix.
True, yeah.
So in FastAI, when we do MNIST, it's usually 64 rows as the mini batch size.
So you can generalize this by taking, I guess, a mini batch could consist of I guess, so it won't be. So yeah, you're right. When we do row operations, this isn't going to be 10,000. It's going to be 64 for one, for a mini batch, or 32 or whatever.
That would be along the column. I mean, the number of
that would be along the rows.
So
along the rows.
X's,
64 by 784. 784 pixels.
Right, that's correct.
Oh, okay, right. But in this case, the dimension of each example is n.
That's right.
Sorry. That's right. Yes. That's right. So when you multiply by a batch, you're actually multiplying by an arrangement of x's, row vectors, and so you could arrange them in a matrix. So this becomes a matrix product, but it still works. Because it's this n that's tied to this n. The number of columns of the input has to be the same as the number of rows of the matrix that it's multiplying. But the number of rows of this matrix, there's no restriction on it. It can have as many rows as you want. So that makes it very easy to generalize this whole thing into into grouping together a bunch of examples in a batch. And then the whole notation that we've just developed carries all the way through. The z becomes then also two-dimensional, and it might have a reduced number of. It might not have to have the same dimension as this, but it'll also in general have 2 dimensions here. or maybe not. Let's see, maybe you're going to map all of these examples into a single row. Have to think about that. But the point is that this notation is really a nice way of thinking about neural networks. That is putting the X first and the weight matrix second, because it allows you to think about chaining together several layers of neural networks to make the whole thing. Okay, somebody asked a question about the activation function described here as a ReLU. Can we say this generalized to all activation? Yeah, in general, it does, because activation functions are element by element operations. That is, they operate, in other words, when you take the ReLU of some matrix, or of some vector, you're taking the ReLU individually of every element of that vector, right? So it doesn't matter, when you take the activation function of a vector, you're applying that activation function to each component of the vector separately, right? And so this is a general statement. You could substitute ReLU for any of the other activation functions, like somebody mentioned here, sigmoids, tanh, or whatever that you want to use. So yeah, that's a good question. This doesn't have to be the ReLU. It could be any activation function. No other questions? Okay, so we've gone long. I intended to go to 12. I'm glad. I'm really thanking everyone for sticking with us till we went to half an hour longer, but I think we all got a lot out of this. Thank you all for showing up. I'm really excited to see all the people that that came, and I think this is a really useful thing for us to go through at any stage of your career. You know, and if you're just starting out, or if you've been using neural networks for a long time successfully, even if you've been a working data scientist, not all working data scientists know this stuff. And the ones who do are much more valuable than the ones who don't. So let's all become the ones who do. Let's quit now, and I'll see you again next Sunday. Thank you all.